Okay. Good evening, everyone. Greetings to you based on your time zone. It's really great to be here again. And today we have another master class, and Mr. Matt Alas will be the one taking us. Is a geospatial specialist, and he works with Dev Global. So he's going to be taking us through the section, but before I bring him up, I quickly want to do some brief introduction, how we usually do. So you can do all to introduce your name, wherever you're joining from. Okay. Okay. So this is the topic. I quickly want to talk about the academy itself. Alright, so let's go. Welcome once again to Precision Agriculture Incubation Program. And the organizer of this program is called Precision Field Academy. So Precision Field Academy is an arm of Integrated Area Precision, an agricultural drone technology company in Nigeria. So it's an educational arm which takes care of professional drone pilot training and digital agriculture training in the concept of agriculture. So what's a vision? At Precision Field Academy, we have a vision to create a world where every young person, regardless of their background, has the opportunity to become a digitally savvy farmer, agricultural professional, driving sustainable and equitable growth in their communities through the transformative power of technology. And our mission is to raise the next generation farmers that are tech inclined and digitally savvy. So Precision Field Academy is a social enterprise where we train and build the capacity of young professionals in modern and emerging technologies for the future of work and to lead with precision agriculture. So what's our methodology? Organizational methodology three, basically. We have the education and knowledge sharing. Secondly, we have the training and skill development, we have coaching and mentorship. And aside from this, we have certain tech skill in focus, in which professional trainings and courses are tailored around them. We have drone technology, we have GIS and remote sensing, we have data science and agriculture, robotics and Internet of Things, machine learning and AI, then enterprise development. All these courses have the way they are related to agriculture and how they can help enhance agriculture. So we have various courses and trainings around under this program that speaks directly into all of these topics and headlines. So why do we do what we do? Our motivation, there's a skill gap that needs to be closed. This is from what we discovered through our research, and we are actually building young professionals to be able to acquire technical skill and enterprise skill that makes them relevant in the future of work in agriculture. So also observing the trend is not enough, not just being amazed or getting updated about the revolution taking place, the industries, the new technologies springing up. Youth directly need to be involved, they need to be an enabler of this technology. And lastly, technology is the key to unlock African agricultural potential. So with technology, data-driven agriculture is possible, and it's more sustainable and profitable practicing data-driven agriculture. So why should you join us? We are creating a future we want in agriculture, and also we connect you to the world of information and opportunities in terms of scholarship, internship and volunteership scale on both local and international scale for your career growth. Also, we cherish skill development through project collaboration, community interaction, university workshops, and symposiums. And also, you have access to coaching and mentorship from industry leaders and professionals around the world. So at Precision Feed Academy, we are building a community of young tech inclined and digitally savvy farmers and professionals. So these are courses we have in relation to AI machine learning enterprise development. So for this program, we have partners, and our partners, we say thank you for giving us a hand of support. So Integrated Air Precision, like you mentioned earlier, a Nigerian agricultural drone company. Here is also a partner. Dev Global, speaker for today, actually comes from Dev Global, so we receive support from Dev Global as well. DJ Academy, Dev Afrique, ISPA, there's International Society for Precision Agriculture. We have African Association for Precision Agriculture as well. And likewise, the three institutions that are below, that's where we're going to be hosting a physical or on-site edition of this program, which is Federal University of Agriculture, Abeokuta, River State University in Port Harcourt, and also for the northern part is Federal University of Technology, Mina, that's FUTMINA. So these are the face of our global faculties. Some of them have already taken their class or observed their session, so while some are still yet to do so. This is the faculties we have for this section or this edition, this particular cohort. So let me quickly talk about this. Okay, so this is the program itself, Precision Agriculture Incubation Program. So I'm just going to quickly talk briefly about it in details, key things that you really need to know about it, and we get going. So this is the program overview. Precision Agriculture Incubation Program, it's a youth-centric digital agriculture capacity building program from the stable of Precision Feed Academy, the classic African digital agriculture training school, causing rapid transformation in the global agriculture sector through comprehensive and expository training expository training of youths on the concept of precision agriculture technologies and its application to solve today's pressing challenges emerging in the agricultural landscape, to strengthen and stabilize economic prosperity. So also recognizing the transformative potential of precision agriculture. So there is an urgent need to equip the young emerging farmers or agricultural professionals and aspiring agripreneurs who fall into the demography of youths with the need for requisite knowledge and skill to harness these technologies effectively for global exploits and opportunities. So the Precision Agriculture Incubation Program addresses the need by providing comprehensive training in these key areas such as drone technology, GIS and remote sensing, data science, robotics, Internet of Things, AI and machine learning, personal and corporate branding, and also drone business and entrepreneurship. So through this program, previous cohorts, we've had participants are empowered to embrace innovation, optimize farm management practices, and contribute to the overall advancement of the agricultural sector by creating a local content digital solution. So during the course of this program, you're going to be engaged with, for the on-site edition, so you're going to engage in some practicals on relating to IoT and also drone technology majorly. So what's our 7 objective? We have 7 objectives basically. So number 1 is to close the knowledge and the skill gap of participants about precision agriculture technologies and practice. Secondly is to raise the next generation of agricultural remote pilots. Thirdly is to groom young precision agriculture leaders and stakeholders for global exploit. Fourth is to build the capacity of youth in the aspect of technology application in agriculture. 5 is to promote the adoption of innovative and sustainable farming technologies to improve agricultural productivity and resource management. 6 is to foster entrepreneurship and encourage participants to develop technology-driven solutions for agricultural challenges. And 7th, which is the last on objective in is to create a network of digitally empowered young agricultural professionals who can drive positive change in the agricultural industry. So the end goal of what we are trying to achieve, this is the objective, or like a principle that guides everything we are trying to do or trying to achieve, yes, with Precision Agriculture Incubation Program, ensuring that we have young agricultural professionals who are with updated knowledge about emerging technologies taking place in the agricultural industry, and how they are well equipped with the knowledge to be able to harness it and interact it to solve problem majorly. So this program also reflects on social empowerment. So, and for the aspect of social empowerment, you have the capacity building. We also have gender inclusivity, policy advocacy, and research. So the capacity building is to ensure you have the skill, both the technical, enterprise skill, and the soft skill. For gender inclusivity, we are encouraging females to also apply. So this program is not only permitting males alone. So females are greatly encouraged to apply. Yes. So we have policy advocacy. Youths coming to programs like this, they are exposed to technologies, and when they have the opportunity maybe to be in the government or to, they will be able to do what I would term as responsible representation in terms of the policy advocacy and regulations that promotes the use of digital technology in agriculture. And lastly is research and innovation. So this program, during the course of the training, you are going to be engaged with different activities, from reading books, also doing independent courses, making research that relates to agriculture in order to increase your knowledge bank on the concept of digital agriculture. And lastly, so we have the training mode. The training mode is taking place in virtual classroom lessons. So the training mode, the virtual/online master classes, is what we are observing now. So after the master classes, we are going to be going for the on-site. For those who qualified, yes, so I will just encourage you to put your best foot forward, ensure that you are doing the very best, so you be able to get shortlisted for the on-site. So during the on-site section, we have the classroom and the physical. The classroom section is you receive some instructions in the classroom before going to the field, to perform through the field experience. So the focus area on the technology is drones, GIS and remote sensing, AI, and data science, robotics and Internet of Things. Then we have personal and enterprise development for hard tech innovators. It's about the business side of things, or market research. So, alright, so without wasting much of our time, let me bring this up. And this is the subject we are discussing today, satellite and remote sensing technology in agriculture. So let me quickly read through our speaker's profile as I bring him on board. Alright, so our speaker for today is Matt Alas. He's a Dev Global Geospatial Practice Manager. So Matt Alas is a passionate geospatial professional dedicated to advancing the health of our planet and its global citizen through the power of remotely sensed data. His journey began in high school when he first encountered the Landsat program, sparking a lifelong interest in satellite-based health monitoring. So over the past decade, Matt has built a distinguished career across both the geospatial software sector through his work with XLIS and /ARIS and the satellite data and product space with digital global and product space with digital globe /MAXA. These experiences have brought him full circle, returning to his foundational passion for satellite data and how it can be used to address some of the world's most complex and urgent challenges. So he is currently serving as the manager of geospatial practice as Dev Global. So Mark leads effort focused on harnessing open data, open tools, and fostering collaborative communities of practice. His portfolio spans key global development across global health, particularly on neglected tropical disease (NTD), regenerative agriculture and sustainable food system, so urban resilience and city planning. So Mark, okay, bridging the gap, bridging the digital divide through equitable geospatial access. So Mark believes we are approaching a critical tipping point where increased data availability, computing power, and institutional awareness of geospatial intelligence can create real impact. However, he emphasized that much work remains in empowering local communities to access and use these tools for decision making and resilient building. So, let's explore how we can use this technology to create equitable and sustainable solution for a better global society. That's one reason. That's one. Okay, that's resilient to today and tomorrow challenges. Okay, that's just saying. Okay, you should be joining us now. I'm bringing him on board. Okay. Hello. Okay. I thank you very much.
Hey there.
So come. Okay, let me just bring up the slide so that you can get started. All right. So you have the floor now. You can go ahead.
Okay, great. So you'll advance the slides for me, Joseph?
No problem. No problem. I
Got
will do
it.
that.
Thank you, sir. Just moving
All right.
around
No
some
problem. So
screens. All right, everyone. Thank you all so much. I wanted to first say thank you for taking time out of your busy days. It's wonderful to be here. It's an honor to be speaking to you all about a subject that I'm very passionate about, and that's remote sensing, and specifically how that applies to precision agriculture. So thank you, everyone. And we'll kind of jump into it. We got a lot to cover. So you can go to the next slide, Joseph. Cool. Yeah, you can flip to the next one as well. Oh, sorry, and past this one. I realized, Joseph, I should have edited the presentation a bit more. Wonderful. All right, thank you all. So today, what we will discuss is the history of remote sensing, various types of remote sensing methods, applications for my firm, Dev Global Partners. We also work with Dev Afrique, but also many of the use cases that we'll discuss are also completely applicable to some of the work that I think you all do, and definitely some of the work that Femi has told me about. So next slide. All right. So let's start from the beginning, huh? So remote sensing actually dates back to over 150 years old. The first initial instances of remote sensing, they actually attached early days cameras, and this is, basically happening in the 1870s and 1880s, 1890s. They would attach these cameras to pigeons. And they would actually have the pigeons basically fly. So much like they used pigeons to carry messages, between locations as a form of communication. They then used kind of the same set, the same trained pigeon, shall we say, to actually take images from above the Earth's surface. So really, that's kind of the defining concept around remote sensing is you are taking an image of an object or of a landscape kind of from an above ground view. You can have an oblique view as well, but basically raised above whatever feature you're trying to identify. So the first aerial photograph that was actually captured from an airplane was taken by Wilbur Wright, none other than one of the two guys who invented the airplane. Um, The images you see in the top right, those are actually images captured from those carrier pigeons with the cameras. Then the bottom right is also an image, but that was captured from an air balloon. So those were kind of the common methods, of course, before we had, full blown flight, of course, many, many decades before we had the drones, which you all use. So initially, those primary use cases that remote sensing supported were kind of in the military and the agriculture domains. Next slide. So the planes were good, but we needed an even higher vantage point. And really, when remote sensing exploded, that came along at the same time as what's known as the space race. So essentially, the race to launch satellites, land on the moon, orbit different planetary objects. That was between the United States and the Soviet Union. So that, of course, was taking place basically from the end of World War II all the way through the Cold War. So while, of course, that resulted in many, many issues, the thing that I think is important to keep in mind about some of those conflicts is typically that comes with a lot of investment and funding into defense spending. And so the defense spending in this aspect in the space race was heavily dedicated towards optimizing how you can launch objects into orbit, both in the Earth surface for the Earth orbit as well as the lunar orbit. So the first ever successful satellite launch was Sputnik 1. That was launched on October 4th, 1957. That was not an Earth observation satellite. It was actually just really kind of a test bed to see if they could even get something into orbit and have it stay in orbit for a period of time. So while the first satellite launch was 1957, the actual first meteorological and what we could call Earth observation satellite was launched in 1960. So we can basically say that we have, a 65-year time span where we've actually been taking images of the Earth's surface from space. One of the biggest data sets available. One of the most impactful federal programs that's ever been launched in this remote sensing space is Landsat. Many of you all will know about Landsat. We're actually currently on Landsat 9. If you flip back, the first Landsat sensor was launched in 1972, which was the first successful US satellite strictly for Earth observation. And it has actually been continuously operational for the 53 years since the first one was launched. So that's a pretty incredible data archive that you can use to do these sort of decadal studies to see how things are changing. And you could be monitoring how ice is changing on the Earth's surface, how agriculture lands are changing, how water resources are changing, of course, how urban areas, which have changed so significantly in these last 50 and 60 years. And when we think about satellite sort of data collection and satellite operations, really you categorize this into three distinct buckets. So there is what's called LEO, that's the acronym, it's low Earth orbit. There's roughly 88% of the currently 12,000 total satellites that are active. That means that those are like basically still being operated. They're still either, pulling down data and communicating with the Earth. So there's basically 12,000 active satellites, many of those of which, as you probably all will guess, are Starlink satellites now, as kind of this new space internet revolution is really in the high gear. So low Earth orbit, typically when we talk about Earth observation data, and we're talking about Landsat here, we're talking about Sentinel, we're talking about, the Maxar satellites, the Airbus satellites, the Planet satellites, those are all within this low Earth orbit. And we bring that up because, you basically are only roughly 500 to 1,000 kilometers above the Earth's surface. So that allows you to take these really accurate, really high resolution images of the Earth's surface. When you get into mid Earth orbit, that is what's known as MEO, only about 2% of all satellites are there. And then the other really critical kind of bucket of satellites, satellite orbital position is known as geostationary orbit. Geostationary orbit is hypercritical for meteorological data sets as well as telecommunications data sets. So when you think about for the NASA program, we have a series of satellites called GOES, GOESS. Those are basically the satellites that allow our National Weather Service, our National Hurricane Center, those types of like critical sort of, disaster readiness and response organizations we have in the US. Those are all leveraging geostationary orbits. And the reason it's important is because you think about a geostationary, the reason it's called geostationary is if you have the Earth right here, you have the satellite right here. Say, for example, the satellite is looking at the top of my hand, which is, for our example, North America. Geostationary means that as the Earth orbits, that satellite is orbiting exactly in time with the Earth so that you're always looking at the same place on Earth. And the reason that that's important from a meteorological perspective is you can basically see these major storms start to form. For us, it's oftentimes in the Atlantic or it could be in the Caribbean, but these kind of, consistent imaging over hemispheres, entire hemispheres of the world, is what allows us to have an early warning and an understanding of where major weather systems might be moving in. And this could be hurricanes, this could be major precipitation events that could bring on flooding. This could be major snowstorms, major, tornado and lightning storms that come through. So I think that's a critical thing for you all just to know is when we talk about satellite data, most of the time, if you're looking at high resolution imagery, it's going to be low Earth orbit. Geostationary orbit, like I said, is telecommunications as well as meteorological. Next slide, please. All right. So when we think about remote sensing, it's a really broad sort of scientific discipline. So you can remotely sense from a pigeon, like we said. You can also remotely sense from a satellite. You can do that as well from a drone and a plane. So those are all kind of the common vehicle types, or what people might call the bus type. And then the common sensor types that we have, and this is where we start to get into the fun stuff, is panchromatic, multispectral, hyperspectral, synthetic aperture radar, and then Lidar. And Lidar is known as light detection and ranging. In a little bit, you guys can look at these images in more detail, but just wanted to show you all, and I assume we'll share the slides, all of the currently active as well as future planned Earth observation satellites that are being, designed and launched and operated by both NASA and the European Space Agency, ESA. Those are captured in the bottom right. So it shows a really amazing sort of like long tail vision of how we're going to continue to collect this really crucial data to monitor changes on the Earth's surface. The final really critical point when you think about remote sensing is the type of sensor that is working. So there's kind of two general categories within that. One is a passive sensor, the other is an active sensor. So as you guys can see here in the image at the top, an active sensor means that the satellite or the plane or the drone is equipped with a sensor that is actually emitting its own energy from that sensor. And then it's basically bouncing off the surface of the Earth, coming back to that sensor. And that reading is going to tell you something. So synthetic aperture radar is a very common active sensor type where it's actually emitting its own power. Lidar is another active sensor type. When you look at common electro-optical data sets, so this would be Landsat, Sentinel, Maxar's, constellation, Planet's constellation, and what you guys do on the drones, you guys are doing passive sensor data collection. So passive means that you need the power of the sun and the light from the sun to actually emit the radiation that then is reflecting off the surface of the Earth, and how that reflection then bounces back and comes back to the sensor that you're working with. That inherently is the aspect of remote sensing. So you are remotely sensing the amount of basically uh, radiation, solar radiation that is coming from the sun, hitting the Earth, coming back through the atmosphere for satellites and then getting to the sensor. One of the great things about drones and plane data collection is you all don't have to worry as much about atmospheric correction. And we'll get into that in a little bit, but that's a very critical component of remote sensing, is making sure that you're trying to negate as much of the effects of the atmosphere as possible. Got it. I see somebody said slow down. Thank you. I can move a little bit too fast. As you can tell, I'm a little eager with this stuff. So thank you. Please comment again if I haven't slowed down. But Joseph, you can move to the next slide, sir. All right, can you, it might not be updating on my, thank you, sir. Okay. Um, so this is really where we get into what I call kind of the science fiction of this whole discipline of remote sensing. And this, in my opinion, for you all, especially at kind of like this stage of your learning, this is really what got me excited and got me interested into remote sensing, because essentially what we're able to do with the different kind of spectral bands that a remote sensing sensor has is we're able to actually see things that the human eyes cannot. So when you all are typically activating and utilizing drones, most drones are collecting images in a few bands. Those bands are typically red, green, and blue. That is what's called the visible range of the electromagnetic spectrum, and that's of course also what our eyes see. So when you take out your phone and you take a picture with that, that is going to feed you back a picture that is captured in this red, green, and blue in this visible sort of range of light. If you all, and I don't know if you're able to like like zoom in here a little bit, Joseph, into the slide, but it would be a little helpful if you zoomed into the visible light section. If not, I understand. It sounds like folks said it's a little blurry. Um, So when you guys look at this electromagnetic spectrum, if you see kind of the rainbow bar, towards the middle of this, that is the visible sort of range of light that human eyes can actually see. But everything to the right of that rainbow sort of section, everything to the left, there is still data. Essentially, there's still stuff happening both on the Earth's surface as well as sort of out in space, and our eyes cannot see that, but you can build sensors that can detect changes, that can detect basically emissions in those ranges. So if you kind of look even closer, you see in the black line, it says radio waves on the left, microwaves, infrared, ultraviolet, X-rays, and gamma waves, all the way, through that kind of spectrum. The very, very tiny sliver that we can actually see with our eyes is between this infrared and ultraviolet. Now, one of the bands that are oftentimes attached to a drone sensor, especially for precision agriculture, those will be in the near infrared range. So those will basically be larger wavelengths than our eyes can see, but we have sensors that can basically capture that. So a good way to think about this, y'all, is basically the tighter the wavelength, the higher the energy is, the lower the wavelength, and kind of the longer the wavelength. What you see on the left side, that's a lower energy. There's benefits to this though. So without getting into too much detail, one of the reasons that synthetic aperture radar is so great is because it does not get impacted by clouds. Clouds are basically the biggest issue that you have when you're doing satellite remote sensing, because as you guys can see in this visible light range, there's all these, it says atmospheric opaque to wavelengths, or atmosphere opaque to wavelengths. So what that essentially means is that the Earth's atmosphere is actually going to block the reflectance of photons that's happening in these ranges, and so you just can't see what's happening, because of how the atmosphere works and how light reflects off of it. So synthetic aperture radar is designed to basically work outside of that range. So if you had a sensor like Landsat that took a picture of a cloudy area, you wouldn't be able to see anything but the clouds. If you have a synthetic aperture radar sensor over that same area, as long as the clouds are not too dense, then synthetic aperture radar can actually penetrate those clouds, still have a signal that hits the surface of the Earth and bounces back up. So it's a really critical data set that is really still pretty new, I would say, but is highly important, especially in agriculture use cases, because of course the rainy season and kind of precipitation is so crucial to agriculture. So I don't want to get too far in there, but I want to spark some interest there, everyone, that you guys are learning about drones and you're learning about this wonderful new science, but there's so many other applications, even moving outside of drones, that can make your work even more impactful. Okay, so synthetic aperture radar, as I mentioned before, everyone, in the top left here, we see a good example of what I was talking about. So an optical image taken over the same area. On the left side is optical. We see clouds, so we can't see anything. That same area at the same time, there was a synthetic aperture radar collection, and it's able to penetrate those clouds. So it's really crucial. The bottom left shows your kind of potential SAR applications, SAR being the acronym. That's, sea ice and glacier changes, measuring rainfall. You can do really important things like tracking ships for logistical sort of purposes, monitoring oil well, those sort of things. And an image on the right, that is essentially what a synthetic aperture radar image will look like. So they are very different to what electro-optical looks like. And there's a lot of hard science behind there, but I hope this kind of sparks some interest from the team. Next slide. So Lidar, as I mentioned, the other very common sensor. Lidar is light detection and ranging. And essentially what happens, and you can have Lidar collections that'll happen from drones, they'll happen from planes. They've also put them on board the International Space Station, so they can be space-based as well. Essentially what's happening is the sensor, say it's sitting, on the basically sitting right here on whatever vehicle it is, it's sending out laser pulses incredibly fast, right? Like millions and millions of laser pulses every second. And basically, say for example, you're in this area in the top right, the laser is in some ways able to penetrate canopy depending on basically kind of like the setup that they have for the lidar sensor, and it can penetrate the canopy, get down to the surface of the earth, and then bounce back up. What this does is paint a pretty much perfect 3D representation of what it looks like, below that sensor. So what you guys can see in the bottom left, one of the very common uses for LiDAR data is understanding the canopy height, which you can determine by basically subtracting the digital surface model, what's known as a DSM. So that's like everything, the height of everything on the Earth's surface, trees, buildings, bridges, etc., and then subtracting that from the digital terrain model, which is the actual like the Earth's surface itself. So you have, the Earth here, you have a building up here. This portion, that height, that's the digital surface model. Just the land is the digital terrain model. The difference between that, right, in this case would be the building height, but you could take it, for example, with canopy height. And in your guys' cases, you could take this for the vegetation height. And those types of insights can help you understand, are you close to kind of prime harvest, which you would, of course, then combine with other data sets. Next slide, sir. All right, but we're now coming back to the space that you all are working in most directly, and that is the common electro-optical sensor types. So that would be the panchromatic, which I've called PAN up here in the top left, multispectral, which is known as MSI, and then hyperspectral, which is known as HSI. So the far left image here is what's known as a panchromatic image. That basically means that it's a grayscale image. So as opposed to you capturing data across the different, color bands that we saw in that electromagnetic spectrum view, you're capturing a much wider sort of range. when you look at multispectral, they have built the sensors so that specific basically readers on the sensor are only taking in light that is within a certain wavelength range. And so multispectral will almost always have a red, green, and blue color channel, like you guys can see here. Like I mentioned, it typically will then have a near infrared, at least one of those, and likely some others. And you basically, what you're actually doing is collecting kind of like three distinct images at the same time in these different channels. And then you can overlay those images. So that's what we see here right in the middle, where we have our red sort of filter, our green filter, and our blue filter captured over these channels. And then when you overlay them together, that's what we visualize below as a multispectral image. So then you're basically allowed to see what the human eye would see if you were looking at that same area. Hyperspectral is the same concept of multispectral, but we can get into that later. So go back, whoop, go back a few. We're going really forward. Go back the other way. Um, Sorry, yeah, keep going back. Back, back, back. Keep going. No, keep going. Sorry. You got it. There was there was basically the slide that we were just on with those three color channels. Like keep going back. Just go to the one right after it. So a little bit more. Okay. Now go to the next one. Okay, great. So um so essentially everyone, when we talk about remotely sensed data, there's kind of again these like three primary aspects of remote sensing data that is going to tell you what you can do with that data set. So the first concept is spatial resolution. You can think about this as what is the smallest thing that I can see in that image. Better spatial resolution typically means a smaller pixel size. So with drones, you all are typically collecting data that's in like 3 centimeters, 5 centimeters, 10 centimeters per pixel. So that means that you can see really, really fine scale things with a drone image, right? Like, for example, one of the tests is you could actually pretty well see the all of the windows on a car, like the windshield, the side windows. With a drone you can see that very crisp, very clear, right? You can read actually, like if they have stop written on the road for a stop sign, you can read that quite well. So good spatial resolution means a small pixel size. Spectral resolution, how many different ways can I see this thing? That's what we were just talking about, was what are the different spectral bands that are being used? So can I see the near infrared? And near infrared is hypercritical for your work, everyone, because there is a lot that happens in agriculture and in plants in that near infrared range. And why remote sensing is so critical is because humans can't see that with our eyes, but there's a lot happening that our eyes can't see that can tell us the quality, the health, et cetera, of the vegetation that we're looking at. And then the last component is temporal resolution. That's the time scale. So how often can I see this thing? So next slide. So spectral resolution, we'll go through this somewhat quickly, y'all. But I wanted to put out the note that if anyone has questions here, there's a bunch of great resources. I'm also happy to answer any questions. So when we look at spectral resolution, a multispectral sensor, which is on the left side, Landsat 8, that has 8 bands. So if you guys look at the graph in the bottom left, there's basically 8 different sort of data nodes that make up that graph that you see. Um, and the area that we're looking at in the bottom left is the same as the area just to the right of it. And that's the one that says Avarice 224 bands. That is a hyperspectral sensor. So the great thing about remote sensing is like we're looking at the same area on the Earth's surface. In the multispectral, we have not that many data points, right? There's not that many spectral bands to tell us what that feature is. If you use a hyperspectral, then you have many, many more data points. There's a lot finer detail where you can better identify specifically what is covered in that specific image, over that area. Why that's important for you all in remotes in drone technology is because when you look at this image on the far right side, there's basically, different sort of spectral signatures and ways in which vegetation should look at different stages of the growing cycle. The important thing too, y'all, just to note is like not only is this helpful for the vegetation itself, this can be really helpful for the soil health as well. So the moral of the story is with spectral resolution, like the more spectral bands you have, typically the easier it is to derive helpful insights from that. So it's commonly thought that more spectral bands is better, but that's not kind of like an end all be all. So you guys can ask questions at the end. So next slide, sir. All right, spatial resolution. Here's a really easy way to see it. So, panchromatic typically actually has the best spatial resolution. There's an inverse relationship between how spatial resolution and spectral resolution work. So, typically, as you capture less bands, you can capture a more crisp, a better resolution image. And we see that in practice right here. So the pan chromatic on the far left, we can see everything in really, really good detail, right? We see all these blocks, we see the separation of detail on that kind of, like rainbow-ish fan looking thing in the bottom right of the or in this kind of right side of the image. Then we lose spatial resolution as we move to their other sensor, and so you see things get a little bit more blurry. And then we go over one more right again, and while that is another panchromatic band, it was built it was built in the past, so it's not as good. And so it's also really sort of pixely. It's highly pixelated, so it's harder to see the difference, right? Especially when you look at that sort of fan looking thing in the bottom right, the discrepancy between the black and the white is much more challenging to see. Then we look at the far right, and that is the lowest spatial resolution we see in this image. And we can see we've lost like pretty much all ability to do any sort of separation of those black and white lines that are right next to each other. Next slide. And this is where it's hypercritical for vegetation use cases. Temporal resolution is the frequency of images that you are collecting. This is one of the benefits of satellites is that those satellites are in orbit, right? And so they are imaging all the time. So you don't need to make a plan to say, I want an image every X number of days because the orbital path is already set. So Landsat and Sentinel, they have a guaranteed sort of revisit timeline of when, for example, they'd come over Lagos. For Sentinel, it's usually like it could be 10, it could be 15 days, depending on your location on the Earth's surface. But that means that every 10 or 15 days, you're guaranteed to have a new image. That can be really good for these kind of longer scale changes. When you think about agriculture, right, the green up process, those are like much, much finer time scale changes on the Earth's surface and changes for the plants. So the higher resolution data set, aka the more frequent images, would be crucial for agriculture. And that's where drones can be beneficial because you could fly a drone on your own and you could say, okay, we need an image every 3 days, we can't do it every 15 days. And so then you are the one actually going out making those collections. And so you, as the drone operator, and basically based on the flight plan and the project plan, you would be the one defining with your customers, your clients, what have you, like what is the temporal resolution that they most need. Next slide, sir. Okay, so why does this matter? The science is cool, but what does this actually do? The entire concept, the crux of remote sensing is to, of course, provide data, provide insights from this data. So what is commonly referred to in this space are data derivatives. So data derivatives are essentially the products that you can generate off of the raw pixels that have been collected by the sensor. So in our case, we're talking about drones. So here's a really good use case where you guys can see the benefits of multi-temporal, aka more frequent collections, as well as the data derivatives that can be created from a a multispectral data set. So what we see here in the image is the top row of these images. That's the early growth. The middle row is the mid growth, and the final is the early flowering. So what we see, then look at kind of the first column. So the true color image, the one that looks like something our eyes would see, and you're seeing early growth, mid growth, early flowering. That's like what your human eyes would see, but there's a lot more happening, in that image that our eyes cannot pick up. And that's where a drone sensor with near infrared would be able to detect, a lot of these more nuanced changes. So, what I'd like to bring your attention to, for example, is the first image, right? It looks kind of similar, just different sort of coloring. We see this big, what looks like kind of an old riverbed that's cutting through the image towards the bottom. That's quite prominent, in the next image that we have on the right, which is an normalized difference vegetation index, an NDVI. That's kind of the one of the most crucial data derivatives that are generated for vegetation and for agriculture. And it's a very, very easy process. I see a question that was, what basic skills should I learn first? You guys could create an NDVI off an image within 10 minutes, with a little bit of training. And the thing is that data derivatives are allowing us to see much more fine scale changes than we would normally otherwise. And that is basically like the primary value of why drones are helpful in agriculture is they can cover very large areas very quickly, and they can also help to identify regions that might be underwatered. They might be identifying regions that are overwatered. They could be identifying pest and disease early on. They could be used to actually start to estimate what yield may be over a certain region. So next one. All right. So how do I do it? So what do I use to make these sort of data derivatives? You all have probably heard of Esri, given kind of your participation in this project. If not, Esri is like one of the oldest remote sensing and GIS companies on the earth. They make the Arc suite, so that would be like Arc Map, Arc Online, all these different things. They are, world class from a GIS perspective. There's other tools like Envy and Erdos and Socket GXP. Those are all paid. What I would recommend for everyone here, if you want to get into this, and honestly, it's a great tool to use the data that you guys will collect from drones, is QGIS. QGIS is free. It can function on relatively low powered laptops, and it's a user interface based tool to actually, analyze these data and to build maps essentially. There's many more ways and more robust ways to work with remotely sensed data when you go into the coding space. So coding based analysis where you don't have, a user interface. It allows for a lot more flexibility and a lot of kind of, specific tweaking on the types of outputs that you want to generate. What I would recommend to everyone is if this stuff is sounding interesting, there's really, really good free tutorials on Google Earth Engine. And Google Earth Engine, you all should be able to get free access for at least a small period. And there's a bunch of training out there that can teach you how to take an image from Landsat and do an analysis to understand the health of vegetation in an area. So there's really kind of like entry level activities that you all can do so that this starts to feel a little bit more real. Next slide. Okay, so taking this into action. Um, so there on the far left of the screen here, that's a true color image. So looking over imagine that you're standing on top of the drone, right? As it's flying over this area, you look down, that's exactly what your eyes would see. Now, in this project, we needed to detect water bodies over these areas to help with guinea worm eradication. And so you can apply one of these spectral indices. Before we talked about normalized difference vegetation index, that's NDVI. That's very helpful for vegetation. There is a similar index called normalized difference water index, NDWI, that allows you to detect water bodies in an image very, very easily. So that process basically, so we can go from the true color image, what our eyes would see on the left, to then what does this math tell us? What does this spatial index tell us? And these blue regions that we see that are very, very kind of distinct from the rest of the image, those are the water bodies themselves. When we then zoom in a little bit further on the right, we can actually see the range of data values that are associated with these different color pixels. So the area that we're okay, and I see people are asking, so I'm just going to respond to this right now. People are asking what a pixel is. A pixel is like one single piece of an image. So if you all, for example, go into, like, you have your own headshot, right? You have a headshot that you have on your computer. If you opened it in an application like Photoshop or something like that, and you zoom in as far as you can possibly go, you'll start to see these blocks basically in the image. And so each of those blocks is a pixel. And so a pixel is basically like millions, tens of millions, thousands of these pixels is what makes up an entire image. So, for example, like the image on the far left, that's just a huge sort of like mosaic of these pixels that are together, that are next to each other, and that's just how we need to kind of visualize it in a computer sense. So we can talk about that more. That might be confusing, but think about the pixel as like a component of the image. Exactly, and people are saying, like, the tiny dots that make up the representation of an image in the computer's memory, perfect. That's exactly the case. Um, so in this case, y'all, so we've kind of gone through the science piece of it, right? We have a true color image, but we have a near infrared band. So that means that we can effectively identify the water. So that is our NDWI raw output on the far left. Then in the middle, we're going to basically start to massage the numbers there so we can make a really nice, clean final map. So that is what we see on the far right. So slide to the next, sir. So this is basically the final map that, we've generated for some of our past clients, and this is essentially the identification of water bodies that would potentially be transmitting guinea worm in this region. And so, the whole concept of remote sensing, right, is like you're finding these cool insights, but the real value is then, of course, giving the people who care about this information that insight in a usable manner. And in this case, right, the teams needed printout maps so that they could actually navigate, personally kind of walk, drive in some cases, but mainly walk to these locations and test the water to see if it contains the copepod that transmits guinea worm. So that was kind of the entire use case. So the science means nothing if you're not coupled with the actual group of people that are going to make a decision based on what you've told them with the data. So you all in your drone capacity, like, you're providing data that then a farmer or another group would use to decide, for example, what types of crops they should farm in an area. When should they harvest? Where should they add extra fertilizer? Where have they over fertilized? Where have they underwatered? Right? Those are kind of the actual um those are like the pieces of information, the insights that are actually the value add to your future customers and clients. So next slide. Here's just a little bit more of a zoomed in view. This shows the water bodies in a little bit more detail. And then through all of this also, one of the great things about remote sensing is based on the quality of detections that you did, you can then basically provide a confidence to that. So again, like, you all need to be thinking constantly about, how is this data going to be most effectively used by the people that I'm using it for, or that I'm collecting it for. And in this case, they wanted to understand, okay, if we have one person going to this area and there's 200 water bodies, and they're only going to be able to visit 100 of them, then which are the 100 highest priority, the highest likelihood, to contain the thing that we want to study? And that's basically like what confidence thresholding can do. It's a very, very critical and very helpful component, especially in agriculture. All right, next slide, sir. I think we just have a few more. I don't know how many more. I'll check. Oh, great. Okay, I think we're actually basically at it. So one more slide, Joseph. Not sure if there's a latency issue. Yeah, we have like there's one slide, Joseph, that has a bunch of links to different resources. It should be the second to last slide. All right, I'm not sure. I'm not sure if anyone else. Yeah, I'm just seeing a blank screen, Joseph. Hello. Just wanted to confirm that you guys can hear me. Okay. Okay. I can see you now, Joseph.
Okay, let me try and bring up the slide. I think it's a network glitch. So
Got it.
that kicked us out of the. So sorry.
It's okay. It's this. Yeah, the second to last slide.
This?
One more, please. Great. So these are free, openly available resources that everyone can access. There are a bunch of very, very helpful, what I would call the first bullet. That's again kind of a foundational, like use case oriented kind of read through. There's not a lot of like actual kind of workshop, hands-on work there. The other three bullets, those are all actually hands-on, and those are also free, so you can access those as long as you have an internet connection. But I would strongly encourage anyone who's interested, start kind of in this order, and you're going to have a really big head start. The final image, if you want to go to the last slide, this is just a bit of a silly one, but what I wanted to educate folks on too is the fact that so this image is also remote sensing. So remote sensing is, for our cases, typically like terrestrial, right? AKA looking at the Earth. There's the entire field of astronomy, right? That is also remote sensing, but it's not pointing the camera at us, it's pointing the camera out. And so just like we use near infrared to tell us how vegetation health is changing, scientists and astronomers use near infrared to see what the structure of like stars are like. And so that's what this image is. It's called the Pillars of Creation. It's one of the most famous astronomy photos of all time. And you could basically, using the skills that you will learn through remote sensing, you could analyze an image of a vegetation plot just as easily as you can analyze an image, of our star system. So I just thought that's interesting.
Okay. Thank you so much. I think we've finally come to the end of the presentation. So I quickly want to check if we have any question for you during the course of the
I think there were a
presentation.
lot.
Okay. Okay, I think this is a question here. The person is asking, what is scope of coverage for mapping delivery in remote sensing operation?
Um, It depends. I mean, people will generate maps of the entire globe, right? So the European Space Agency releases a land cover data set that has basically the classification in 10-meter pixel sizes over the entire Earth's surface. Typically, when you're delivering like like a map or a series of maps to people, it's going to be a much smaller scale. So really the scope of coverage, it can be entirely global, or it can be hyper local down to like a city street, a few city blocks.
Okay, thank you. I'm still trying to check for others. By the way, thank you so much for your excellent presentation. You really drive the point home, and it's a bit practical delivery. So, this person is asking, Michael's, that can you integrate both the vector and the raster data formats in the same map delivery report? So, you have
Yes,
anything to say to
absolutely.
this?
Joseph, go back 2 slides. So, yeah, perfect. Either one. So the short answer, Scarlett, is yes, 100%. You absolutely can integrate vector and raster formats in the same map delivery. That's exactly what we're seeing here. So the base map, which is what's commonly like that's the common term, for these sort of delivered maps, that's the true color image. So that's where we see the river, kind of on the right side. We see the kind of burnt out land on the left side. That's the raster data that sits at kind of the bottom of the image. All of the colored polygons and points, those are all the vectors, right? So the blue polygons, those are all the water bodies. The points are, known water bodies that they have, but 100% Scarlet, you can.
Okay, thank you very much. I quickly want to go to another question, so because of our time, so I don't. What kind of crops or problems are best monitored using satellite technology?
Yeah. Um, and Joseph, do you want to go on mute while I answer? I think there's a little. Oh.
Forward or backward?
No, no, if you want to mute your microphone while I respond,
Okay,
because
to
there's
avoid
an
echo.
echo. Yeah, great. So thank you for the question. What kinds of crops? Um, the what I would say the easiest crop type or more agricultural setup that you would have for remote sensing is monocropping, right? So that's one single plant type across a huge area, and that's because satellites are typically capturing the pixels are not as small, and so you can't see as small of things. So the reason that monocropping is good for that is because you have wheat, for like multiple hectares, hundreds of hectares. And so that means that you can really effectively capture that whole area and do a really good assessment of that vegetation, knowing that there's not a lot of other vegetation types within it. The reason that drones are hypercritical, so not satellite technology, but still remote sensing technology, is because of the smaller pixel size. You can look at these multi-cropped areas and you can still identify crop types, whereas a satellite may not be able to make that sort of delineation between crop types. Then the so generally speaking, like the problems that are best monitoring that are best monitored using satellite technology, it's many things, but I would say the safer answer is like large scale, so very large area and longer timeline changes in the earth's surface, so monitoring glacier changes, monitoring wet reservoir heights, monitoring urban growth. Those are things that when they take a lot of time and they're covering a big area, that's like the best sort of use case for satellite data. But you can still use satellite data for much finer scale things. Cool. We can go to the next question. All right, how can remote sensing data be integrated with GIS for farm mapping and planning? Also, who owns the data collected after it's been analyzed? A wonderful series of questions. Um, So the short answer to your first question is QGIS. So the map that you guys still see on the screen right here was made entirely with that free software, QGIS. So that I would say is like the tool to, integrate the imagery and the vectors that you have to create a map. But there's other ways to do it. And then who owns the data collected? That's a really complex question. If you own your own drone and you are flying in an area that it's not um, It's not managed or anything like that by the government, and you're just allowed to fly it over a beach or something like that, right? Like that's your image. You own that. When you're working with satellite data, you are oftentimes only licensing access to that data. So the reason that I've mainly focused on the federal assets is that those, while they are still technically owned by NASA or owned by the European Space Agency, they allow the data to be used free and openly. So, like, they still technically own it, but you can use it for any sort of application that you want. You don't have to pay anybody. You can make these awesome derived products and then actually sell them to other people. That is for NASA and ESA. That's a specific segment of federal sort of, managed assets. When you look at other satellite companies like Planet, like Maxar, like Airbus, they own all of those images. And when you have to buy a certain image that they've collected, and you then don't actually own it. You are just simply getting a license, buying a license from them to use it either perpetually, so forever, or for a certain period of time. Okay. Okay, the NDWI image. No, go back the other way to like those final maps close to where we were at the end. Right. Yeah. So is it is it this one that you were talking about, Scarlett, or was it the one before? Um, okay. So we'll just go we'll just go with this one. The short answer is up in the top right of this. So this image, correct? Sorry, it's always fun doing Q&A.
Hello. I don't know. Probably is this image or the other one because there are two
Yeah,
images there.
you
But
can
she's
you can
asking
stay
like
here.
the one at
Yeah.
the top right corner. I think it should be this. She's asking if it's a water
Yeah.
body. So.
So basically those two light blue regions that are just south of the road, you see the road kind of cutting like this across the image, those are both water bodies that we detected.
Okay, okay. She confirmed yes. That
Yep.
that's the
All right, we got some more questions. Um, so again, like this is a great question, but a complex question. Um, you wouldn't use a remote sense. You wouldn't use a remote sensor to really like to try to predict earthquakes, right? And you definitely wouldn't use an electro-optical to detect things on the Earth's surface. So that's a really critical component to remember here, y'all, is that like what we are seeing from a drone, just like what we are seeing from a satellite, is simply the light that is reflected off the surface of the Earth and then back to that sensor. You are not looking below ground. You would use to understand like the material that's underneath. There's another, it is still remote sensing, but it's not in our space. It's called ground penetrating radar, GPR. You would use ground penetrating radar to do basically this raw material identification. But I will say quickly, like there are still surface deposits that you can view from a satellite that then might tell you that, hey, there's a likelier chance that these types of minerals or resources exist underneath because of how that kind of landscape looks with those surface deposits. So we can go to the next question. What ways can data be trained? Yeah, wonderful, wonderful, wonderful question here. It's not totally solved, but there are definitely tools out there. There's data lakes. Maybe you all are aware of Digital Earth Africa. So DEA, Digital Earth Africa. It's a large kind of data warehouse that's dedicated to um, African continent specific data sets. So that potentially could be a good tool where you can reach out to them and say, hey, I have this data. I'd love to upload it. There's also other open tools out there where you can just kind of like upload your drone data to kind of the open community. Um, so I would need to Google. I can't exactly recall the name of it, but if you were to Google like free drone imagery, there should be a few websites out there. You would just want to be sure, back to the licensing and ownership question, as long as it's your image, you can do whatever you want with it. Just make sure it's not something that a client paid you to collect, and now you're going to kind of open it up to other people. All right. Yeah. So Lisu, great question. What I would say is if you can solve this question, you will have a very profitable future. This is inherently like the crux, I would say, of what the Gates Foundation, what the CG centers, what so many of these institutions and your national governments, they want to solve this question. So data science, in my opinion, how can it help farmers determine the most profitable crops? Like, that's not just a remote sensing question, right? There's a bunch of market intelligence data that is required for you to make that determination. So that would be understanding at the local market level, right, nearby wherever this farm is, like how are those prices changing on whatever crop you're talking about. And if it's not something that you're distributing locally to a market there, are you distributing through a co-op, are you distributing through kind of a larger national network? Those like historical cost trends, and predicted future cost trends, those are a critical component, because just like, just analyzing an image and saying, here's a bunch of really healthy wheat, and I think that I'm going to export, or I'm going to harvest, this number of kilograms, like that is just one piece of the equation, right? The actual then viable cost that you can get, and how that changes based on the proximity to the farm, all those things, like you can see where I'm coming from, that this is an unbelievably complex question, that we are working hard to help solve. But like I mentioned, man, if you can tackle it, well done. Saw some questions on like climate, which are really critical. I mean, keep rolling, Joseph. You can keep rolling through the questions. Mm, Rama two, great question. Okay, so we're gonna get a little nerdier than I had planned. So the active sensors, don't think about it them producing their own light. They are not. So they are producing like energy in a specific range of the electromagnetic spectrum. So synthetic aperture radar, right? It's synthetic aperture radar. So it emits radar waves. If you were to think back, if you can go back to that electromagnetic spectrum slide, Joseph, where it was like kind of that one that had like the one single huge image on the screen. It should be back like 5 or 6 slides. Um, that those sensors, they are not. Yeah, keep going. I'll tell you in a sec. A little bit more, a little bit more, more. I think one more. Perfect. Okay. No, back. Yeah, perfect. Thank you, sir. So like these active sensors, they're not emitting their own light. They're putting out more or less a radio wave from the sensor that then is traveling down and hitting the surface of the earth. So that means that they do not require light. So synthetic aperture radar, one of the best benefits of it is it can image in the day, it can image in the night, any time of day. Electro optical, so the drones that you all have, right, and the satellites that I use, those require sunlight. If it's dark out, they don't work, right? Like you can still use it to some extent, but your ability to detect things is massively reduced. There is kind of a subset of nighttime imagery, but in terms of actually like assessing vegetation health, you're not going to be able to do a lot of useful agricultural insights if you're imaging at night. Next question. Okay. Joy, great question. Can remote sensing be applicable to animal husbandry as much as it is in crop science or agronomy? The I don't know if as helpful, if I would say that, but it is still helpful. Um, so there's a lot of different like use cases out there for animal husbandry, right? One example was, part of the work that we did to detect those water bodies could actually be used to tell nomadic farmers or even farmers who just let their animals graze in a more open range, like that information of where the water exists could absolutely be shared with them so that they can then go to those water bodies and have their cows or goats or whatever use that as a water source. So that's kind of one example. There's a use case in the US. It's a little macabre. It's a little gross where like you can actually use really good resolution imagery to count the number of cows in these giant cattle pens that we have, and they can actually use that for commodities trading. So they can actually like image these massive ranches in the United States and in Brazil and get an idea of how many cows are in that area, and then they can actually these mathematicians and finance people will use that to then make an inference on like what the potential price of beef is going to be in the coming months. So I know that sounds really crazy, and that's like again like a much larger scale thing. But just wanted to let you know that there are applications for it, but I wouldn't say that they are as useful, as crop science and agronomy. What are some emerging trends? James, thank you for the questions. What are some emerging trends or future opportunities in remote sensing for agriculture, research, and business? Oh man, so many, I would say. Um, it's kind of a tough spot, like of where to begin. Um, the emerging trends, I mean, really honestly, y'all, the biggest emerging trend in our space right now is of course artificial intelligence and how quickly that can help people make new data insights from different or make new insights from different data sets. So the emerging technology, the emerging trend, I would say, is the multimodal sort of concept where you guys are collecting drone imagery, and that's awesome, but there's satellite data that's also being collected. Then you could also potentially incorporate ground level data. So you could actually have someone out there, collecting soil samples and understanding what's the nitrogen, what's the phosphorus, what's the potassium content in the soil, and weaving all of those different data collections together. So starting at the ground and then using drone for a really high resolution and then using a satellite to have kind of a broader view, like that combination of data sets and what that tells you is a really I wouldn't even call it emerging. I mean, that's kind of like the crux of remote sensing. But with your entire continent, the African continent, people starting to become more connected to the internet and to technology, like I would say African people have this wonderful opportunity at your hands right now to assist not only in this drone data collection, but one of the things that satellite companies so desperately need is that ground truth, is like the field level, like human on the ground sort of validation of what that satellite is collecting and indicating whether or not, say, for example, you take a satellite image, you classify an entire, village and all their farm parcels, and you say, okay, I think it's 70% wheat and it's 20% maize and it's 10%, sorghum or something like that. A farmer or the community would then go out and actually take readings and take pictures and do all that stuff that then actually truly like counts and validates what that looks like. That sort of interplay of people on the ground and you all living in those communities and collecting that accurate data and then improving what the AI models and the analysis is saying, because you guys are basically correcting it when it's wrong, you're saying it's right when it is right, like your insight is helping to make those data derivatives more accurate, which then inherently should provide for better decisions to say, again, this is, we need to change our crop from this type to that type, oh, there's like a pest in this area, those sort of other insights. I hope that's helpful. Felix, you're getting to a really, really critical point, man, that a lot of people don't talk about as openly. The question, Felix, is does it imply that this technology cannot be effective in monitoring crop indices in an intercropped field? I won't say that means it's not effective, but I will say that it makes it much more challenging, and you need to really be confident, in your methodology of how you're trying to go about this. This is where drones, as I mentioned before, have a huge value proposition on the African continent because especially because from what I'm reading, right, it seems like some of my colleagues in Kenya and other places are moving back to a more traditional sort of approach, right? Where like there was this huge push to say, let's plant wheat everywhere because wheat's going to make us a bunch of money. And that was great. And that happened for a while, but it degraded the soil. And then also, obviously, with certain sort of pests and disease, it could wipe out entire villages, entire massive, harvest. Now that from what again I'm reading with my colleagues in Kenya is that you're kind of moving back to say, multi-cropping is what we need to do. We need to kind of balance the risk of potential pest and disease. We need to make sure that we're having nutritious meals. Like that is where drones are crucial because drones have a good enough spatial resolution where you can accept crop types. Felix, I will say, and feel free to message me after, like there are nuances beyond that because, of course, as you probably know, there are cover crops where a cover crop, if it is truly covering like the new seedlings that are being grown, then the drone is not going to be able to see that, right? The drone is going to have to stop, you're going to hit that cover crop. It's not going to penetrate below and you're not going to see the seedlings. But not all multi-cropping, of course, uses kind of cover crop approaches. So I hope that was helpful, my friend. And I'm not trying to sell you on anything because what you're asking is I think one of the biggest problems that we can solve with drone technology. All right. Salisu, another great question. Can these technologies be used to monitor the carbon footprint of agriculture activities on a large scale? Short answer is 100% yes. Absolutely. There are numerous NASA missions and European Space Agency missions that are dedicated specifically to this. And to actually monitoring sort of carbon exchange across the surface of the earth and specifically of course into agricultural areas. So I would, if you honestly put that same question into ChatGPT or into a Google search, it'll tell you the different sensors operated by NASA and ESA that are directly focused on that. uh, awesome. So great question, Ibrahim. Can remote sensing be used for soil moisture monitoring and how accurate would it be? I will. So first and foremost, absolutely. Soil moisture monitoring is a critical component of remote sensing and can be accomplished with a variety of sensors that are out there. There's actually a NASA mission that was like entirely dedicated to this. It's called SMAP, SMAP, Soil Moisture Active Passive. That sensor was very specifically designed to map and monitor soil moisture across the entire globe. The fun thing too is that so that was one sensor built just for that. Landsat and Sentinel have bands that allow you to do your own sort of soil moisture classification off of a specific image. Soil moisture, I will say, like when the accurate question is a hypercritical one to answer, right? Because again, you need to think about the fact that like when the sensor is leaving the drone, like or when the light is hitting this Earth's surface, coming back up to the drone, like it's not penetrating very deep into that soil, right? So I think that there's, and this is where my expertise will fall down. I would imagine a lot of the accuracy comes down to like the substrate, right? And the soil type that you have. So I'm sure that certain soil types, like they can, hold water really well in like sort of a top region. I would imagine other soil types, it doesn't retain water super well. So that what sensor reading you're getting, I think you would be sure that you would need to like understand that soil structure very well so that you can be confident that you're not like kind of over over prioritizing the soil moisture index that you created, because it might be wrong. So I know that that's not a great question on like the accuracy side, but again, Ibrahim, I would just bring you back to my concept and my idea of like the importance of the field validation level. So, when you guys do these drone collects, like, is there a way to add an additional service that says, hey, and we're also going to go and collect, 20 different soil samples and either try to do a, moisture sort of classification? Are you quantifying, again, the phosphorus, potassium, et cetera? Like, I don't know. I think that there's ways where you guys as drone operators can kind of expand your service offerings, that might be able to increase accuracy. Um, yeah. So this is again a really nuanced question, so Lisa. In what ways can satellite or remote sensing technology help in early detection of crop disease and pest? It can help a lot, right? So I would just say quickly that one of the one of the ways that it can do this is basically, like I mentioned before, mapping the greenness of the vegetation, right? So if you are able to operate a drone over the same farm plot every day, while it was in the seed to kind of, initial sprout and then the green up, like those images that you would capture should allow you to do an earlier detection of the crop disease and pest, because the greenness is going to differ in kind of the growth, the speed of growth will differ across that, and that potentially indicates to you that there might be, a pest or a disease in some points. But there's certain pests and diseases that like you can't really see. So cassava brown streak disease is a great example. I worked on a project that was focused on mapping that. You cannot see cassava brown streak disease from a sensor. You need to cut it open, basically. There's like certain aspects of the leaf and like how it can start to decay where you can kind of get some idea, but to be 100% confident it is cassava brown streak disease or cassava mosaic virus, you need to cut into it. So remote sensing, one of the other important things I want you all to know, this is not like the solution for everything, right? Like there is still a hypercritical ecosystem of soil scientists and climate scientists and the like that are required to make this all happen, because remote sensing is not just going to solve all of your problems.
This is the last
Yeah,
question. After this, we wrap up the session. Thank you so much for your time so far. It's highly
absolutely.
appreciated.
Yeah, I hope
So,
this was helpful. I hope I'm not just droning on. Okay, so what are the limitations of SAR in agriculture remote sensing? Um, I'll be honest, Peter, it's a great question. I'm not the SAR expert. I would call it dangerous with SAR, but I'm not at all a SAR expert. I am a multispectral, hyperspectral, et cetera. But what I would say from my knowledge is, you're probably, I mean, the big thing is that you're missing the near infrared range, right? And that's like when we look here in this image right here, Peter, right to the left of the rainbow, the visible light, there is so much happening, like between how water is, basically like being used by plants and then, potentially released, like, aspirated. It's how carbon dioxide is exchanging, it's how nitrogen is exchanging. All of those very fine scale sort of like changes in the profile, the electromagnetic profile, that will not be captured by synthetic aperture radar. So while you can still look through clouds, my opinion is that with synthetic aperture radar, the great thing for vegetation is that you can still monitor basically the height of how that vegetation is growing even when it's cloudy. But if you want to start to get into assessing like the health of it, that's where you need, the electro optical aspect.
okay, thank you so much, sir. Thank you so much for honoring the invitation. Thank you so much for coming. I've also learned a lot from your section, and it's powerful, it's mind blowing, and very, very insightful. Thank you so much, Mr. Matt. Yes, so on behalf of the Precision Field Academy team. I'm extending greetings to you. It's such an honor to have you here. So, okay, we'll be closing now. So, I just want you to share with our participants maybe any word of encouragement you have for them during the course of their learning. Anything, like a final note to share with them. Yes.
Oh yeah. Um, can you mute really quick, just so it doesn't echo?
Okay, you need the slide?
No, no. If you could mute so it doesn't echo.
Okay.
Yeah. What I want to say is you all should feel very proud, and you should feel very excited and encouraged by you taking this leap and trying to work into a new technology. It is incredible. There is so much opportunity. You are supported by a great team at Precision Agriculture, right? With Femi and his team. So I just wanted to say ask a lot of questions. And those questions are not stupid. This space is hard. There are people who go to school for decades to be experts in this, but most of those people are nice and most of those people want to share that information. The online community of remote sensing is really, really strong. And the amount of people that want to help others understand this technology and make better use of it, like, is vast. So I would say go into this, feel free to ask any question that you have of these folks, and you'll find the right people that are going to try to help you. And I would just say, stay focused on this. The opportunity with drone technology, with GIS, with artificial intelligence is huge on the African continent. So bravo, hats off. I wish you all the best of luck. Thank you so much.
Very
You're still
much.
muted. Yeah, yeah.
It's really great to have you here. I wish you had a very good evening at your hand. All right. Thank you very
Wonderful.
much. Bye for now. All right.
Thank you all.
See you. Have a great time. Bye. All right. Okay, so to all our participants, so this is just to quickly give you a briefing that tomorrow we are going to be having another class. It's two sections to be precise. A class on that's IoT, a bit of robotics and IoT, and the other is focusing majorly on AI, like, okay, artificial intelligence, will artificial intelligence replace human, or what's the balance between them, the disparity, like, is AI taking over human or human is taking over? So yeah, we'll get to see more light about that tomorrow in tomorrow's section, because we have two class, the morning and the evening section. So put that in mind. The information will be shared on the group and also on via the emails for those who we open the registration portal later for. Just for the late registration, because I'm hearing that the group is filled up with something now, so I have to create a new group. So if you have not joined the other group, so the information we're going to send out, you'll be able to join the new group so that you can also be on the group. So for those who are presently on the group, you don't need to join the new group link that will be sent out, so that it's going to be easy for coordination. So thank you everyone for joining. I believe you are also learning and getting exposed to this digital technologies. The future of precision agriculture is propitious, especially when young people or youths are well informed about this technology. We are in a digital age, or the jet age, where everything is moving at the speed of light. So get this knowledge accurately. You can also volunteer, do internship with research organizations, yeah, just make notes to them, collaborate with them, work with them. Through that, you will be able to build more skill, get on hands-on project that you can do to intensify and consolidate your learning experience. So beyond the Precision Agriculture Incubation Program, the learning curve still keeps evolving. So you don't just need to fold your hands after this program. Just keep learning, keep making research as well. So just ensure that you are growing gradually. So ensure you put your best feet forward. After this class, the attendance link is going to be sent out. So for those people who participated, you'll be able to sign it, so we'll be able to record that you attend, because all of this is very very crucial for your admission to the second stage, which is the on-site and all of that. So because there are so many things we are also going to consider and look for before choosing people to participate. However, you are still learning on these digital technologies from our global faculties. So the issue with the link, because most of the link we'll be sending out, even for the independent course link, the attendance link, people have been complaining that okay, they're having issues with it, the link is not going through. I would advise it's just a network glitch, nothing more, because people actually complain to me that the links are not working, or some of the complaints we have in the other group with my other team members. It's that same link they made use of to actually still get the certificate for the program. So I think maybe at the time you're trying it, it's just a network issue. You can do well to use another browser. If you're using Chrome or Phoenix, or there are different browsers, just try it on different browsers first. So, and you can also maybe give it a time interval, maybe 1 hour to 2 hours interval. So you try it again, so you'll be able to work. So because for the courses, those are the links we've been using to even in the previous cohort. So, and since we are not going to create the course directly, so it's created by some other third parties, but actually using part of their resources as well in order to consolidate this program and ensure that we all have a good outcome. So I would just advise that you take it easy. When you have a network glitch, maybe you can try it later. So all the links are working. So, and the attendance link will also be open so that everybody will be able to have their entries easily without any problem. All right, thank you so much for staying till this time. So it's really a great pleasure to have you all here. So looking forward to tomorrow's sections, the master classes then. Yes, so all right, thank you. Do have a good evening, or bye for now.